In this lecture, we'll look at the first two quantifier rules for proofs. We're going to need all of the same rules from propositional logic, so those are all implied here, and I just want to look at the two new rules that we're going to add on top of those 10 that we had before. So we have an existential quantifier out rule and a universal quantifier out rule in this lecture. And if you look at it closely, you'll see sort of a consistency between these proof rules and our truth tree rules from the previous lecture. What I mean by that is if we look at the rule for an existential out quantifier, the whole idea of an existential out quantifier is that we can get rid of the quantifier and put it in a constant for our variable as long as that constant doesn't appear somewhere else in the proof. So here, as the rule is constructed, since there's an A next to this Q, I have to pick something different. So I just pick B. And if you look at the universal quantifier out rule, it's unrestricted. So from this universal quantifier, I can put in any constant that I want, even if it appears before in the proof. So with the truth tree rules, if you had an existential quantifier on the left-hand side, you had to pick a constant that doesn't appear anywhere in the truth tree before. And if you had a universal quantifier on the left-hand side of a truth tree, you could pick anything that you want. So same rules apply here. Existential quantifiers are limited, and the universal quantifiers are not. The process with using these quantifier out rules are the same for one-place predicates and two-place predicates, but we'll just start by looking at only one-place predicates. The proof structure in predicate logic is the same as in propositional logic. So we have these four different columns. These numbers are keeping track of our assumptions. Then we have our line numbers, which will just continuously go down. Then we have our derivations here in this third column, and then our justifications here in this fourth column. So same exact process as before. We're just going to try to take our assumptions and derive our conclusion based on the rules that we have. So based on what we've got here, we've got a universally quantified statement, and we have one in which we have a PA, not a PA from before, but a P predicate with an A constant. And so we're trying to get to QA here. Like with the truth trees, when we had an unrestricted quantifier, it was nice to always just pick whatever constant already appears in the proof because that's the best way to get something to match. So what I'm going to do here in line 3 is I'm going to get rid of this universal quantifier by placing an A in for all of the X variables. So everywhere that I find an X, I'm just going to put an A in for it. Now, hopefully you can see this just looks like our arrow out rule from before. I've got an arrow or a conditional statement. I've got its left side up here. So in line 4, I can write the consequent in my derivations. What am I getting that from? I'm getting from 3, which is my conditional, and 2, which is my antecedent, and then that way I can get my consequent from that. And then we're just adding together our assumption numbers over here, what number's next to 2, 2, what number's next to 1, 1, and so that's all it is. This one's a little bit more complex, so if we look at what we have here, we have one assumption with an existential quantifier. That's going to be restricted, so that should immediately make you think I need to do that before I do anything else because I need to pick something that doesn't appear in the proof. And then we look at our conclusion. What's the main operator in our conclusion? Well, that's the tilde here. So if a tilde is your main operator in your conclusion, you should immediately be thinking what? You should be thinking I'm going to take the opposite of that conclusion, so the conclusion minus the negation, as a PA and look for a contradiction. So that's what we're going to do. We're going to assume the opposite of the conclusion here as a PA, and then we're going to try to build a contradiction. So as I said before, since this existential quantifier is limited, we should get rid of the quantifier first there, and I'll just choose A because there are no constants that appear prior to line 3, so PA and tilde QA, and hopefully you can see where we're going here. We've got the tilde QA. We should be able to make a QA from this line 2 up here. Before getting that, though, I just separated out the tilde QA from line 3 using our 3 and out rule, and then I get the QA from up here in 2. So remember, with the universal quantifier, it's unrestricted. What's going to be advantageous for me to get as my constant here in my derivation of my universal quantifier out rule? Well, it's going to be A, because now I've got something that's an actual contradiction. I just have to piece them together with my ampersand in rule. So 4 and 5, putting them together, ampersand in. What numbers are next to 4 and 5? 1 and 2. That's why we have 1 and 2 here. Now, I made a PA. I derived a contradiction, so I can add or take away a tilde from that PA. And so that's what I'm going to do here. I'm going to add a tilde to my PA, and that gets us our conclusion. And the only thing you have to remember is to eliminate the assumption number associated with the PA here in the far left. Okay, I'm going to give you an opportunity to pause the video and then try this one out on your own. Okay, so looking at what we have here, we have only one assumption, and we're just trying to derive just two simple statements here, PB and QA. So remember, when we have an ampersand as our conclusion, we're just looking to derive one conjunct and then the other conjunct, and then we could just put them together with our ampersand in rule. Now, looking at our assumption here, what's the main operator? Well, the main operator here is the ampersand. It's holding together this universal quantified statement and this universal quantified statement. How we know that is that there aren't any parentheses closing this off. This quantifier only goes to the extent of P, and this one only goes to the extent of Q. So what we have to do first is we have to separate out both of these conjuncts. So we're just going to do one and out to get both of these derivations, and then it should be pretty straightforward. What I need is PB and I need QA, so I'm just gonna take these statements or these quantifiers, and since they're universal, I can put in whatever I want, and so I'll choose PB for line 2, and then I'll choose QA for line 5, and then I'll put those two together in the final step here. Okay, again, I'll give you the opportunity to pause the video if you want to try this one out on your own. Okay, looking at what we have here, we've got one universally quantified statement, so that's unrestricted. That's good because it looks like we have, well, I guess two different types of constants. We have an A and a B. So we'll come back to that here in a second. Looking at our other two assumptions, no quantifier, so we don't really have to worry about anything there. RB, does it appear somewhere in the proof? Well, yes, it does. It appears right there. So really all we need to do is get this arrow out. With that, why don't we start by getting rid of this universal quantifier, because the universal quantifier, we've got PA and QA already in this proof, so P and Q, I think having an A would be helpful in this situation. So we'll get rid of the X variable and replace it with an A constant using our universal out rule on line 1. Now we have a double arrow, so remember the double arrow is actually two single arrows in disguise. So why don't we use our double arrow out rule to get PA arrow QA, because what we really need to get this conditional statement out is this left side. I've already got the PA, so I need to get the QA to be able to build this antecedent. So if I get this biconditional out and create this conditional statement, I've got the left side of this conditional statement, which means I can get the right side of it through 3 and 5 arrow out. What number's next to 3? 3. What number's next to 5? 1. So that's why we got 1 and 3 over here. Now I've got PA and QA. I can piece them together using my &n rule from 3 and 6. And now I've got the antecedent to my conditional statement up here that's holding my RB hostage. So I can get RB by doing 2 and 7 arrow out. That brings in 2, and then 1 and 3 as well. So that's why we get 1, 2, and 3. Okay, again, I'll give you the opportunity to pause this video if you want to try this one out on your own. All right, looking at what we have here, we've got 2 universally quantified statements in lines 1 and 2 from our assumptions. Looking at our conclusion, what's the main operator? Well, the main operator is this tilde. So that should immediately be telling you, assume the opposite, try to build a contradiction. And so that's what we're going to do here in line 3. We're going to assume EX, PX, and RX. And we get this statement. And now, evaluating what we have here in our first 3 lines, we've got 3 different quantified statements. The first 2 are universally quantified, so those are unrestricted. Then I've got an existential quantified statement here in line 3. That one is restricted, so I should get this one out first, and that's what I'm going to do. I'm going to just pick A because it doesn't appear up above, using my existential out rule. Now I can put in any letters that I want for these universal quantifiers, and I'm just going to pick letters that are going to match the ones I just picked. So after I separate these out real quick, I guess I forgot that I did that first. So I'm separating these out with the &out rule. Could have done that after I did the universal quantifier out. Doesn't really matter. Now I'm going to use my universal quantifier out rule to get this first conditional statement. So PA arrow QA. And as you can probably already see, I've got the conditional statement, I've got its left side, its antecedent, so I can get its right side or its consequent from 5 and 7. 1 is next to 7, 3 is next to 5, so that's why we've got 1 and 3 here, using arrow out. Then I'll go back up here to get my other conditional out. I'll just use A's in the place of the X variables again, because those are going to be what matches. Now I've got RA, I've got the conditional statement, so I can get the right side of my conditional statement. So 6 is where my antecedent's at, 9 is where my conditional statement's at. So I can get tilde QA, and look, there's my contradiction pieces. I've got tilde QA, and I've got regular QA, so I'll piece them together. 2 and 3 are next to tilde QA, 1 and 3 are next to regular QA, so 1, 2, and 3, &n. And then based on my contradiction, I have a PA that depends upon it, so I can add a tilde to that PA statement up here. And then the key thing is to get rid of the assumption number associated with that PA. Okay, I'll give you an opportunity to pause the video again and try this one on your own. Okay, looking at what we've got here, we've got a universal quantified statement and we've got existential quantified statement. So there immediately I'm thinking that's restricted, that's unrestricted. So I need to make sure that I do this before I do this. And then we look at our conclusion, which is another tilde. So we're going to have to assume the opposite, just like before, as a PA, and look to build a contradiction. Just like with the previous proof, we have 2 universally quantified statements. So let's save those until we get our existential one out. So here in line 4, that's what we're going to do. We're just going to take our existential quantifier out and put an a in the place of the x variable. And then we can do our first universally quantified statement up here. And again, the whole idea when we're doing this, we want to do the quantifiers that are limited before we do the ones that are unlimited. That way we can get different terms that match within our proof. So here I've got PA wedge QA arrow RA because I'm trying to build a contradiction. Hopefully you can see that that's going to be where my contradiction comes from. I've got a regular RA and I've got tilde RA, so I just need to try to build a contradiction in that way. Now that we have this, we're still looking to get the antecedent of our conditional statement here in line 5. I can start to build it by using my universal quantifier out rule on line 3 here, so I can get a PA, and then hopefully you can see that we can just wedge in the QA on our PA using our wedge in rule here. Then now that I've got the antecedent to my conditional statement, I can derive my consequent, so RA, so 5 and 7, arrow out, 1 is x to 5, 3 is x to 7, good there. So I've got RA, I've got tilde RA, I just need to piece them together using ampersand in. That gives me all my assumption numbers together. I've got a PA, it builds a contradiction. So in line 10, I can add a tilde to this PA up here to get tilde AX PX. So 3 is where my PA is at, 9 is where my contradiction's at. I'm adding a tilde, and then last thing I gotta do is just drop out that PA that's associated with the assumption number 3. I'll give you a chance to pause the video. Alright, looking at what we've got here, we've got an existentially quantified statement as one assumption and a universal as the other, so again you should be thinking I need to get rid of this quantifier first because it's limited and this one is unlimited. Looking at the conclusion here, this one's a little tricky. See if you picked up on it. The main operator is an ampersand. And then the two conjuncts are negated universally quantified statements. So what I'm going to actually have to do here is I'm going to have to derive this first, and then I'm going to derive this second. And how do we derive statements that are negations? Well, we have to assume the opposite and build a contradiction. So what we're going to do after we get rid of our existential quantifier here is we're going to assume the opposite of this conjunct and try to build a contradiction. So that's what we're doing here in line 4. Now, from line 4, we can use our universal quantifier out rule to put in an a for our variable x. Next, we can use our universal quantifier out rule on our second assumption up here to get PA arrow tilde RA. So hopefully you can see this is going to be where we get our contradiction to add a tilde to our PA. The only thing we need is we need to pull the PA from up here in this statement that we used or that we derived once we did our existential out rule. So we've got the PA up here, we just need to bring it down from ampersand out. Now I've got a conditional statement, I've got its left side, so I can get its right side. So tilde RA, so 6 is where conditional is, 7 is where the antecedent is, so I can get the consequent 6 and 7 arrow out from 6 and 7. Now I've got RA, I've got tilde RA. All I need to do is put them together with my ampersand in rule. What number is next to 5 for what number is next to 8, 1 and 2, so that's why it's 1, 2, and 4. Now I can add a tilde to this PA up here, so that's what I'm going to do. So 4 is where my PA is at, 9 is where my contradiction's at, adding a tilde, dropping out the assumption number here, and then I just have to restart. Now I need to derive this tilde universally quantified QX. So I'm going to just assume the opposite. So AX, QX as a PA and look to build another contradiction. So I can just get QA out from doing my universal quantifier out. It's unlimited. Now I'm just trying to find a contradiction. Well, look, there's tilde QA. Here's QA. So I can pull that out of my quantified, or the derivation that I got from the existential quantified statement up here. And so I can piece those two together to build my contradiction. So 12 and 13. And then I can just add a tilde to my PA here in 11. And then finally, we just need to piece together the two conjuncts that we created. So we created one in line 10. We've got one in line 15. So we're just going to ampersand in. And then we get our conclusion. So it's a little involved, but it's just doing half of the proof, or for the conjunct, for one conjunct in our conclusion, and then doing the other half of the proof for the other conjunct. Go ahead and pause the video if you want to try this one on your own. At first, this is going to seem pretty easy because you have 3 universally quantified statements and you're just going for a wedge statement as your conclusion. So you might be thinking, okay, I just need to derive either RA or SA, and then I can just build up the disjunction by wedging in whatever I need at the end. But if you see here in line 1, I've got a wedge statement, so that's probably going to mean we're going to have to do wedge out. So that's going to get pretty long. We have here 3 universal quantifiers, so we can get them out by just putting in whatever constant we want. We're just going to match them up. So first one, I'm just going to pick A's to put in the one place of the one place predicates. And same thing with line 2, same thing with line 3. So now we're done with the universal quantifiers, and we're just doing our normal rules from propositional logic to try to build this statement over here. So remember, to do wedge out, I need 3 things. I need a wedge statement, which is in line 4, and then I need to show that each side of the wedge statement leads to the same conclusion, namely this one here. So we need to assume one disjunct and show that it derives the same conclusion by building a conditional statement, and then then we're going to assume the other disjunct here in this case would be QA, and try to build an arrow where the consequent is the same conclusion. So here we're going to assume PA as a PA. I know that's a little confusing. Maybe I should have been picking different letters for the quantifier out rules, but makes the most sense to me to start with A and then work my way down. So PA of PA, and then we're going to try to build this conclusion here. So I have an arrow statement. I have its left side. So here in line 8, I can get the right side of my arrow. From 5 and 7, arrow out. And then I just need to wedge in my SA on my RA and 8. And so I made an assumption. I got to the consequent that I was looking for, so I can build the arrow like this. That's the first part of this proof, and then now we just need to do the other half, which is I need to assume the QA as a PA and look to build the same conclusion. So I have QA, I have a conditional statement, which means I can get the consequent there, so I can get SA, so 6 and 11. And now I just need to wedge in my RA, to my essay. And now I can build that arrow, so QA arrow, same consequent as before. 11's my PA, 13's my consequent, eliminating my PA number there. And so now I've got my wedge statement. I've got one arrow showing that one disjunct leads to the conclusion. I've got another arrow showing that the other disjunct leads to the same conclusion, so I can affirm the conclusion using my wedge out rule. So the key thing here is, where are the pieces? You might be tempted to cite line 1 because that's originally where this wedge statement came from, but that's not really the wedge statement that we're using to do this wedge out rule. The main operator up here is the universal quantifier. Here it's the wedge. So we need to cite line 4, not line 1, and then we need to cite where our arrow statements are, so 10 and 14. Now we're going to move to two-place predicates. The same rules apply here, so please don't let them scare you. It's just doing the quantifier out rules for the quantifier that's the furthest to the left of the statement. So looking at our first argument here, you can see that I've got one assumption that already has constants in their place. I've got PAB and QAC, so those are not the same, but it doesn't look like it's going to matter here, but we just need to be aware that these are different constants, at least the B and the C in the second place of these two-place predicates are different. And then we got a double arrow R, and then we've got just this two-place predicate with two universal quantifiers out in front. So right now we're trying to derive this R as our conclusion. Double arrow is the main operator here, so you might be thinking that we need to get the double arrow out rule, build a conditional statement in which the R is our consequent, and then we just need to derive whatever this is as our antecedent. And if that's the intuition you had, great job, because that's what we're going to do. So to begin, though, we want to, or sorry, I guess I should say, we know that we need to build this antecedent. So we need PAB wedge QAC. So these universal quantifiers are unrestricted. We just need to get something that's going to match this PAB. The key thing here is that we have to do each quantifier one at a time. So we need to do the universal the universal quantifier with X as a variable first because it's the furthest out. It's got the widest scope. And so we're going to place an A in for our X because that's what we have up here. And then after that, we're going to place a B in for our Y. Now we've got something that matches up here and we're in pretty good shape. Now it's just like a normal propositional logic proof where we're going to wedge in our other disjunct that we're going to need, and then we can use our double arrow out rule here on line 1 to get this statement. Now we have the antecedent to this conditional, so we can just derive R from 5 and 6 arrow out. And so what number does 5 have next to it? 2. What number does 6 have next to it? 1. So we get 1 and 2. We only have 3 more practice problems in this lecture, so I'm going to go ahead and let you pause the video if you want to try it on your own. Okay, looking at what we've got here, we've got, again, one statement that has universal quantifiers attached to it on the outside, and then we have, looks like, another assumption that has a constant fixed to it, and then we've got a conclusion that has other constants fixed in a two-place predicate. So again, don't let this overwhelm you, because immediately you should see that this is a tilde statement, so we need to assume the opposite and try to build a contradiction. That's what we're going to do. So we're going to assume the opposite of our conclusion because it's got a tilde. Look to build a contradiction. Okay, so what do we have here in our universally quantified statement? We're trying to get something to match here. So when we're going to do our universal out rule, we have to do it for the x first. And I'm going to pick the letter B because the letter B is going to be where we get this, or we're going to try to get something that matches this PA here. And so since the x is in the first place of this two-place predicate, we're going to put a B where that x is at. And then we need to put the same B in for this x variable here. So that's why we have PB, Y, QB, and then QY, because the x that was here is getting replaced by a B in those two different places of the statement. Now for our Y, we want to place an A constant in for N. So everywhere that I had an A, or everywhere that I had a Y, I'm going to put an A. So I had a Y here and a Y here. So that Y turns into an A, that Y turns into an A, using my universal quantifier out rule. All right, now it should be pretty straightforward. I've got a conditional statement. I've got the left side of that conditional statement, so I can get the right side. That's what I'm going to do here, using my arrow out rule 1 and 3. And now I've got a conjunction. One of those is going to be part of my contradiction. So I've got this up here. So I'm going to use my ampersand out rule to get this QA from line 6. Once I do that, now I've got the two things I need for my contradiction. I just need to piece them together with my ampersand in rule. I've got a contradiction. Depends upon my PA in 3, so I can just add a tilde to my PA to build tilde PBA with my tilde in rule. And then the key thing is to remove the assumption number here in the far left. Okay, I'll let you pause the video if you want to try this one out on your own. Again, don't let this overwhelm you. So I've got a universally quantified statement as one of my assumptions, so that's unrestricted. That's pretty helpful. There's still two-place predicates, so when we get rid of this universal quantifier, we're going to have to put the same letter in for all of these x's, but we can deal with that later. Now, if you're looking at the conclusion, tilde out in front of those universal quantifiers, so that's the main operator. That should be telling you I need to assume the opposite, try to build a contradiction. So that's what we're going to do in line 2, is we're just going to assume the opposite of all this as a PA and try to build a contradiction. So really doesn't matter which one we do first. I just chose to get rid of the universal quantifier up here in line 1. So I just put in A's for all these X's, so all these X's turn into A's with my quantifier out rule, and then I just broke apart this conjunction, so I just derived the two different conjuncts from line 3. So broke down this first assumption to its simplest parts. Now let's look at the second universally quantified statement up here. So again, the whole idea is to try to get things that match. So for this first universal quantifier, this AX, I'm going to put in A for the places in the predicates where X appears. So I put in an A and an A. Using my universal quantifier out rule. The nice thing about universal quantifiers is you can put in anything that you want. So I can put another A in for this universal quantifier. So everywhere that there was a Y, I'm going to put in an A. And now it's pretty straightforward. I've got a conditional statement. I've got the left side of that conditional statement. So I can get the right side here in 8. That's what I'm going to do with 4 and 7. Now I've got QAA and I've got tilde QAA, so I can just build that as my contradiction in 5 and 8. Now I've got a contradiction, depends upon my PA. and so I can add a tilde to my PA from up here in 2, so 2, 9, tilde n, dropping out that PA that's associated with the, the number that's associated with PA. Sorry about that. Last one, so go ahead and try it on your own if you want to. Looking at our assumptions here, I have an existential quantifier in the second position here, so that's a little worrisome because I know that's going to be restricted, but everything else was a universal quantifier. So universal quantifiers here, there, and then also in my conclusion, which is a negation, so you should immediately be thinking, I'm going to assume the opposite as a PA. Hopefully that's in your mind now. We've done so many of them where that's the case, so we're going to assume the opposite of this conclusion, but this existential quantifier is a little worrying because it's limited. I want to make sure that I get it out as soon as I can. So in line 4, what I'm going to do is I'm going to get rid of the universal quantifier in this statement. So now I have the existential quantifier by itself, or I guess not by itself, but as the lone quantifier left in this statement after I use the universal quantifier out rule. So everywhere that there's an x, I'm going to put an a. That's where we're getting this from. Now for the existential quantifier, I have to pick something that doesn't appear anywhere in the proof. And so I chose b to fill in those y variables there and there. And now it's just all about trying to get these other statements to match what I have in this conditional statement here. So looking at 2, I'm trying to get something that's QAB, so every x I'm going to replace with an a, and then as you can probably guess for the y, I'm going to replace those with a b for the universal quantifier out rule. All right, well that's a good start. I've got something that's got a tilde, and now I just need to derive this consequent from this conditional statement up here, and then I'll be in good shape. I can just build my contradiction and then add a tilde to my PA. So the next step will be to get the universal quantifiers out on this statement up here in 3. So again, what's going to be most advantageous is if I replace the x with an a, because that will match this antecedent, and then I can replace the y variable with a b to get PAB here in line, or from line 8. I can derive that in line 9. So now I have conditional statement, got the left side, so I can get the right side. So 5 and 9, arrow out. And I've got the tilde QAB, I've got the regular QAB, so I can put them together to build my contradiction. Now I've got a contradiction. Depends upon my PA up here in 3. So I can just add a tilde to that PA. So PA up here, contradiction down here, just adding a tilde to this PA. 3 and 11, tilde n, and then dropping out the assumption number associated with the PA. And that's it.